You ever wonder if there's like a hidden blueprint to the world around us? A secret direction or a pattern that kind of governs everything, from how a bridge vibrates in the wind to how your car stereo sounds just right. Well, turns out there is, and today we are going to pull back the curtain and see what it is.
It sounds like a bit of a riddle, doesn't it? I mean, you've got this massive piece of engineering, a super high-stakes geological search, and, a car stereo. At first glance, they have absolutely nothing in common, right? But deep down, they all share this invisible secret, a mathematical idea that shows us how they really work.
And the list just keeps going. This same secret blueprint is absolutely crucial in things like communication theory, analyzing stress on mechanical parts, you name it. It's almost like this universal key that unlocks how complex systems behave. So, what is this incredibly powerful hidden principle?
Okay, let's dive into this thing. To solve this mystery, we got to start with our very first clue, the vector. Now, if you're picturing just a simple little arrow pointing somewhere, well, you're only seeing a tiny piece of the puzzle. The idea is so much bigger than that. So in science, we're usually dealing with two basic kinds of quantities. First up, you've got your scalars. It's just a single number, a magnitude. Like the temperature outside is 20 degrees Celsius. That's it. Simple. A vector, though, is different. It's designed to package together a bunch of related pieces of info.
And here's the big idea. At its heart, a vector is really just a list of numbers. So instead of trying to keep track of the traffic flow on 4 different streets separately, we can just bundle all that data into one single object, this vector, 10, 5, 3, 11. Just like that, we've taken 4 separate numbers and can now treat them as one single thing. It's a ridiculously efficient way to organize information.
Okay, so we've got our data all packaged up nicely inside a vector. But what good is that data just sitting there? We need to be able to do something with it. And this brings us to our second clue, how we can act on that information. For that, we need a special kind of action machine. And in linear algebra, we call that machine a matrix.
So, just think of a matrix as a machine that performs an action. It takes a vector you feed into it, does something to it. Maybe it stretches it, or squishes it, or spins it around, and then it spits out a brand new, totally transformed vector. This whole process, it's called a linear transformation. Let's look at a few things this machine can do.
First on the list is rotation. A matrix can literally grab our vector and just swing it around to a completely new position. Its length might not change, but its direction is now totally different.
Then you've got dilation. In this case, the matrix acts like a scaling tool. It can take a vector and either stretch it way out, making it longer, or shrink it down, making it shorter, all while it keeps pointing along the very same line. And this one's kind of wild. It's called shear. Imagine your vector is just standing straight up, and the matrix transformation just comes along and pushes it over from the side. It actually gets slanted. The bottom stays put, but the top moves, changing its whole orientation. Pretty cool, huh?
So we've seen that when a matrix gets a hold of a vector, that vector usually gets knocked into a totally new direction. It gets twisted, slanted, sent off on a new path. But here it is. This is the crucial question, the one that unlocks this whole mystery. What if a vector goes through this whole transformation machine and comes out pointing in the exact same direction it went in?
And that very question leads us to the big reveal. It turns out, for any transformation, there are these special, unique vectors that are directionally invariant. They don't change course. It's kind of like finding the grain in a piece of wood. No matter how you try to cut it or shape it, the grain is still there, pointing the way. These vectors, they reveal the system's hidden blueprint.
And this special vector? It has a name, of course. It's called an eigenvector. The name actually comes from the German word eigen, which means something like proper or characteristic. And that is exactly what it is. It's a vector that shows you a fundamental, characteristic direction of the system itself. When you apply the transformation, it doesn't get rotated off its axis. It just scales.
Okay, so let's put it side by side. This is the whole ball game right here. You put most vectors through the transformation and bam! They get knocked off course. Their direction changes. But an eigenvector, it holds its line. Its direction is stable. It's intrinsic to the transformation. The only thing that changes is its size. It just gets a bit longer or a bit shorter. And that stability is exactly what makes it so important.
So how in the world does this pretty abstract idea solve our real-world mysteries? Well, we found the special direction. That's the eigenvector. But to complete the puzzle, we also need to know the amount of stretch or shrink that happens in that special direction. And that amount, that's our final clue.
That stretch factor also has a name. It's the eigenvalue. It's just a simple number, a scalar, that tells you exactly how much the eigenvector gets scaled up or down. So if the eigenvector is the what, the characteristic direction, then the eigenvalue is the how much. It puts a number on the strength of the transformation in that one specific direction.
Right, let's bring it all home. Remember that vibrating bridge? Well, engineers can model all the bridge's physical properties as one massive matrix. Then, they find its eigenvectors. And what do they find? The eigenvectors represent the fundamental ways the bridge wants to vibrate, its natural ways of shaking. Then they calculate the eigenvalues that go with them, and those tell them the natural frequencies of those vibrations. And here's the kicker, the biggest eigenvalue. That corresponds to the most dangerous frequency. That's the one. It tells engineers the exact vibration they have to design around to prevent a catastrophic collapse.
And there it is. The secret blueprint is revealed. From bridges to car stereos to finding oil deep underground, eigenvalues and eigenvectors are the tools we use to find the hidden inner workings of a system. They reveal its most critical, characteristic properties, the natural frequencies, the main directions of stress, the most stable ways it can exist. They literally make the invisible structure of a system visible.
By finding these special directions, we can understand, predict, and engineer the world around us with an incredible amount of precision. It just goes to show you that underneath all the complexity on the surface, there are often these simple, really powerful principles at work. So the next time you look at a complex system, just ask yourself, what are the hidden directions, the invisible forces that I might be overlooking?